session in the IMFSE Fire Safety Day lecture series. And normally it's Ruben van Koyle who's doing this introduction, but he asked me to be his stand today, so I'll try to take care of that. My name is Ben Atkinson, and I am the coordinator, program director of the International Master of Science in Fire Safety Engineering, as I'm sure most of you know. And as you also probably know, is that the central theme this year for the Fire Safety Day lecture series is on the use of modeling in the context of fire safety design. And then throughout these lecture series, we are very happy to listen to experts enlightening us on some benefits and some challenges in this use of modeling in the context of fire safety. And this session is no different. I'm very happy to introduce two speakers again. First is Sauca from DBI, and then the second speaker will be Ben Atkinson from Jensen Hughes. And I'll also keep an eye on the clock. So first, I'm very happy to introduce Sauca from DBI Denmark, and she will tell us something on the hybrid fire testing, which is a novel method to do structural fire testing. As usual, we will have a little bit of time for questions after the presentation, and I strongly encourage you, if you have a question during the talk, to already type that question in the chat box, but do not press enter yet, and that because your question might be answered later on in the talk, but if not, then you're ready to ask that question after the presentation, and then you don't need to be shy, and you can ask it straight away. Just for the sake of transparency, I remind you that these sessions are recorded, trusting that nobody is objecting to that. So without further ado, I'm very happy to ask Anna to share her screen so that we can listen to her and enjoy her presentation. Anna, the floor is yours.
Yeah, hello, good evening, everybody. Okay, can you see my presentation now?
I can't see it yet, but maybe it's still coming.
Okay, I'll try again. You see it?
Okay, it's probably me. So
okay, so you can see it.
But if it's thin walled, part of the thin wall assumption is that it doesn't vary very much across that.
Okay,
can I ask everybody to mute your microphones? Please mute your microphones unless your name is Anna.
Okay, so then I will be starting the presentation. Good evening, everyone. And as Bart already said, I will be talking about the hybrid fire testing, which we refer to it as a new structural fire testing method. And before going into the, I'd just like to say a few words about me. So I'm a researcher at DBI, but I've been introduced to this field, to the fire field, when I started my PhD at University of Liège, Belgium. At the same time, I worked as a researcher in Serip, France. And after I ended this period, I went to United States at NIST. And since last year, I'm working at DBI. Okay, so now let's go into the presentation. Here is the outline of the presentation, and I will start introducing the concept of hybrid fire testing. And then we'll give some more details about the hybrid fire testing framework, a brief state of the art, and then we will present a case study, which is a hybrid fire test performed on a prototype gypsum plasterboard-based wall assembly. And of course, we will end with some conclusions and future work. Is everything okay? I keep hearing some voices, so...
Yes, please mute your microphones. Thank you.
Okay. So the introduction. If we want to answer the question how a structure behaves when exposed to fire, from the structural point of view, we will be performing fire tests. Now, the most common way of performing fire tests is to test individual members And these individual members are subjected to simplified mechanical boundary conditions. And when I say mechanical boundary condition, I refer to the end restraints. We also know that this type of testing, we refer to it as a standard testing or member testing. Now, we learn a lot of information from this type of test, but we know that they don't reflect 100% the reality. If you want to learn how a structure behaves in fire and how it would behave in a real fire, then I think the full-scale testing would offer us maybe a proper view about that. And if we perform full-scale tests, then every member is subjected to a real mechanical boundary condition. But as you can imagine, this is a very expensive approach. And here I provide two pictures. One of them is presenting the Cardington test. I think it's one of the most known tests performed on full scale. And one very recent one is the one performed at NIST last year, and the project is still ongoing. Now, hybrid fire testing is a methodology which comes and tries to combine the advantages of the previous two methodologies mentioned. And this means that we want to keep testing individual members because it's easier and cheaper, but we would like to try to provide realistic mechanical boundary conditions. And how do we do that? So imagine that we want to analyze this structure, which is a moment resisting frame. And for this example, I just considered the fire compartment in the last floor, and the beam and the columns are exposed to fire. So now, definitely, let's say that we are interested in how the beam behaves when exposed to fire. So during the hybrid fire testing, if you are interested in the behavior of this element, definitely we want to test this member. But we also want to provide the realistic boundary conditions. And how do we do that? So we divide the global structure, so the moment resisting frame, into two substructures. And the location where we do this division, we refer to it as the interface. And please remember this notion because I will be using it during my presentation quite often. So as I said, we subtract the element that we want to test and we refer to it as a physical substructure. And here you can see just the beam exposed to fire and loaded with the exterior loads. But what is typical to hybrid fire testing is you see that at the interface, we don't allow simplified boundary conditions, such as just simply supported, but instead we provide some actuators. And these actuators, what they do is they take into consideration actually the effect of the surrounding. And this surrounding is the rest of the moment resisting frame, which is modeled aside. So we model this part of the structure using a finite element model, most probably, or other means. And because we are modeling it aside, we refer to it as a numerical substructure. So therefore, in hybrid fire testing, we test individual members, we provide more realistic mechanical boundary conditions, which take into consideration for the effect of the numerical substructure. And more precisely, how is this done? I would like you to imagine this activity as a loop, which is performed continuously during the test. And during this loop, we have several steps that we need to take into consideration. And here are the steps that we need to perform. So we have the physical substructure, which is subjected to fire and to the external loads, plus the actuators. And of course, when the physical substructure starts being subjected to fire, the material will start degrading, and this will lead to the formation of forces and displacements at the interface. So therefore, we have some forces and displacements. Now, what we do is we measure these forces F and displacement U at a certain time step, let's say N. And the measurement is done by using the data acquisition system. And then we go a step further, and now we compute what's happening in the numerical substructure. So we perform the calculation of the finite element model. And then using all the collected data, we are able to provide to compute what is the new force and the new displacement to be updated at the interface. And as you can see here, we have a new time step. So the way we do this calculation is actually what's the hybrid fire testing methodology doing. And I would like you to imagine just a bunch of formulas which do this job. And because we have a short time, I will not go into details. So once we have these values, then we have the transfer system, which at the end there are some actuators, but in hybrid fire testing, let's say world, we call them transfer system. And therefore these the transfer system, so the actuators at the boundary will apply these new forces and displacement. But just because we did the division of the global structure, we always need to be careful that the forces and displacement at the interface of the physical substructure and numerical substructure are in equilibrium and compatibility. Okay, a very brief state of the art. This methodology, hybrid methodology, is widely used in seismic field. Nevertheless, fire is quite specific field, and therefore the direct use of all the developments is not possible, unfortunately. And as a proof, only few hybrid fire tests were performed so far, especially on large-scale specimens. But unfortunately, more field is ongoing. Okay, so then how did we apply this methodology at DBI? We were interested in studying the behavior of gypsum plasterboards based wall assemblies. And here is a short description of these assemblies. They are used in single-story buildings and for internal partitions in multi-story buildings. We know that they provide the passive fire protection as compartmentation elements. And they are typically constructed of steel studs, insulation, and gypsum plasterboards. And as you can all guess, the fire behavior of the wall is highly dependent on the thermomechanical properties of gypsum plasterboard. But at the same time, we also are aware that so far we still are not able to numerically model the gypsum fall-off during the fire test. So if we are the producers of such materials and we want to do some modification inside the material, or we want to develop some new similar materials, then most of the times we will do that based on a trial and error basis. And this will lead to a large number of expensive full-scale fire tests. So we ask ourselves the question, how can we avoid this? How can we study this problem? Just trying to use different glasses on our eyes and try to provide maybe some solution to these problems. And in order to study the problem using the hybrid fire testing, we started with the prototype gypsum plasterboard based wall. Is the one presented in this slide. And as you can see, the wall is composed of the gypsum plasterboard, insulation, and steel studs. And here you can see the front view of the gypsum plasterboards, and the length of this wall was of 950 millimeters, and the wall was wide 200 millimeters. It was 200 millimeters wide, but only 500 millimeters were exposed to fire. And of course, we also provide some thermocouples when we will do the fire test on the unexposed side of the gypsum wall. So, okay, how do we approach this problem using the hybrid fire testing methodology? So here is the wall, and it's exposed to fire. And as we said, the behavior is dependent on the gypsum plasterboard behavior, and we are still not able to properly model the thermomechanical behavior of this material. So therefore, we have no other way than testing this type of element. So therefore, the gypsum plasterboard will represent the physical substructure. Now, the insulation doesn't offer any stiffness from the structural point of view, therefore it will be neglected in the structural analysis, but the steel studs, we know how to model the steel studs at ambient and elevated temperature. So therefore, the steel studs represent our numerical substructure. And because you see that the gypsum plasterboard is fixed to the steel studs on the top and bottom, the problem actually reduces to a 1 degree of freedom problem. It means that the wall is able to expand or contract only in one direction, mainly in one direction. So therefore, when we test the physical substructure, we provide an actuator based on what I explained at the beginning of this presentation. And this actuator will take into account the effect of the numerical substructure. And by having an actuator, of course, we will have some forces and displacement. So then what we do during the test is just make the connection between the physical substructure and numerical substructure. Okay, so now we know what we want to do, but we needed to develop a hybrid fire testing setup in order to do that. And I think this is one of the most challenging parts of the project. The setup, I would like you to see it as two parts. So one of them is made out of an Intel real-time system, and you can read more about it. You can search Google for Intel and you can see what are they doing, and the experimental setup. Now, this system, inside this system, we had the hybrid fire testing coordination algorithm implemented there. And again, those are the bunch of formulas that I were mentioning before. And just to be more precise, in case you want to, I don't know, later on search for more, we use the dynamic relaxation algorithm. Now, this system also is the one responsible with controlling the temperature in the furnace and controlling the displacement on the physical substructure, and of course, processing the digital signal. Now, if we go to the experimental setup, we see that the physical substructure is attached to the loading frame, and the loading frame later on is attached to an electrical furnace. The electrical furnace has dimensions of 500 by 500 square millimeters and is able to provide several heating curves. Okay, so now let us see more into detail the loading frame. How is it composed? So again, the physical substructure is connected to these aluminum profiles. And we also provide some calcium silicate boards, number 2. And we use these boards just because the dimensions, the opening of the furnace were bigger than the dimensions of the physical substructure. So we needed to enclosure the furnace. But I think the most important part of the loading frame is this zoomed area, because this zoomed area actually will allow us to account for the effect of the numerical substructure. So the effect of the steel studs. And as you can see, and remember, I mentioned the fact that we have 1 degree of freedom problem, so therefore we provided one actuator. This actuator will be moving up and down and will be, of course, controlling the displacement of the board, and based on also on what the numerical substructure, on the result provided by the numerical substructure. So we provided the screw actuator, and to measure the displacement, we provide some displacement transducers. And in between the physical substructure and the screw actuator, we have a load cell which will measure the forces built up in the physical substructure. And here I will show you a picture. I won't go into detail here because you will see it later on the same picture, but I would just like you to have an idea of how it really looked like in reality, this loading frame. Okay, so now we developed everything, and we performed an experimental campaign, and this table presents the test matrix. And as you can see here, I will be presenting the results of 4 tests. And we considered 2 parameters during our test. Of course, so again, here we have the picture of the wall. The gypsum plasterboards is tested, is the physical substructure, and the steel studs are the numerical substructure and are modeled. For simplicity, we consider that the steel studs will remain at the ambient temperature, and that's why we represent the behavior of the steel studs by the numerical substructure stiffness. And this is the value that we computed for test 1, 2, and 3. But just to see how important is the effect of the numerical substructure, we also provided the test number 4 with a different value, so in order to be able to observe this effect. Another parameter that we used during our experimental campaign was the time temperature curve that we used in order to heat our specimen. So we considered 3 types of heating curves. One of them was ISO 834. The second one was the ramping curve for 30 minutes up until 600 degrees Celsius, and then holding for 30 minutes at 600 degrees Celsius. And the last heating curve that we considered was the ramping curve up until 400 degrees Celsius for 1 hour. Now, because the test number 1, 2, and 3, they have the same numerical substructure. So the same physical substructure, the same numerical substructure, but different fire exposure. I will be presenting here the results of test 1, 2, and 3. And don't be scared because there are so many graphs. You will see that actually it's easy to understand. So the first column will be presenting the results of test number 1. The second column will be presenting the results of test number 2. And the last one, the results of test number 3. Now, the first row is presenting the temperature type graphs. The second row presents the force time graphs, and the last row presents displacement time graphs. So let us look into the test number 1 to start with. If we look at the temperature evolution in time, we see that we provide what was the target temperature, but also the measured temperature inside the furnace. So we can see that we were able actually to follow the target temperature very well. And at the same time, we provide the temperature on the unexposed side of the physical substructure. Unfortunately, during the test 1, we lost the thermocouple on the unexposed side of the physical substructure, so we recorded only temperatures up until 200 degrees Celsius. Now, if you look at the force versus time graphs, you will notice that I present the force that is built up in the physical substructure, which is the gypsum plaster board, but also what is the force computed on the numerical substructure, which is the steel stud. So the first thing that when we look at this graph, you observe that these forces are symmetrical. This means that equilibrium is satisfied. And this is one of the conditions that we need to fulfill in order to have a successful hybrid fire test. If we look at the displacement evolution in time, again, we plot the displacement on the physical substructure and the displacement of the numerical substructure. Again, by having the same displacement, it means that we fulfill the compatibility at the interface. Therefore, we can say that our test is successful. Now, most of you probably you're asking yourself, why do we have these spikes in the measurement of the physical substructure? And this is because, as you can see, we are controlling very, very small displacements at the interface. And most of the time, the transducer that we are using it for, I don't know, standard tests, they don't really have the best precision to do this control during the hybrid fire. Nonetheless, I think quite good, and the fact that we didn't have instability, we consider that it was a very successful test. So, okay, we noticed that equilibrium and compatibility are fulfilled in all of the tests. And again, as I said, that's very good. But now let us look actually how the gypsum plasterboards behave, because I think this is quite interesting and you won't be finding a lot of data in the literature about it, no? Because most of the time, the gypsum plasterboard is not tested, so we have no idea what type of forces or displacement develop inside the gypsum plasterboard board. So as you can see that at the beginning of the test, the board will start being heated very fast. This means that the specimen, the physical substructure wants to expand, but just because we have some stiffness provided by the numerical substructure, this expansion is blocked. So if we block the expansion, of course, that we will build a high compressive force. But with the time, the specimen starts being heated more and more. Some of the material degrades, and at the same time, it will start shrinking. So therefore, we can see that the compression force is reducing, and moreover, it will build a tensile force. And in the moment when we build a tensile force, we have cracks appearing on the gypsum plaster boards, and these cracks will start opening more and more until the specimen doesn't carry any load. Now, a similar behavior can be observed during the test number 2, but what is specific for the test number 2 is the fact that by providing this heating curve, we are getting the steady state condition across the section. So we have the same temperature in every point. And we kind of have almost similar behavior with the test number 1, is just now we have a lower heating rate. So therefore the peak compressive force, it's happening later in the test, and the same, the compressive force will start decreasing until we build the tensile force, and then we have the failure. And it's interesting to observe that even if we don't have as high temperature as during the test number 1, we still build up quite high forces, and this is because the heating rate is actually very important in terms of the mechanical behavior of gypsum plaster board. And this was well known in the literature, but now we can actually visualize that. During the test number 3, the specimen is heated with low temperatures compared with the previous tests. And as you can see, there is no tensile force built in the specimen. So therefore, during the test number 2, we have no failure. But what is the most interesting, again, that we have the lowest temperature in the test number 3, but nevertheless, we have the highest compressive forces. And again, this is due to the fact that the specimen is heated slower. This means that it has time to absorb the heat, so therefore it will just build up this compressive force. So I think looking at these results, first of all, we have seen that we were able to perform successfully hybrid fire tests, where we take into consideration the effect of the numerical substructure, but at the same time we learn a lot about the thermomechanical behavior of the gypsum plaster boards. Now, here I present the gypsum plaster boards at the end of the test number 2, and you can see the exposed side and also the unexposed side. So you just have an idea how do they look like, and you can see also the crack in the middle of the board. Okay, so now let us look at the importance of the numerical substructure. You remember when I introduced the experimental campaign, I said that in the test number 4, we will be providing just a random value for numerical substructure stiffness in order to observe what is the influence of numerical substructure. And the time temperature curve that we use, it was the same as during the test number 3. So we present 2 graphs, the force versus time and the displacement versus time, and then every graph presents the results from test number 3 and 4, but this time we present the results only from the physical substructure. So as you can see that by reducing the stiffness of the numerical substructure is as if we expected, it means that we allow for larger axial displacements, and by allowing larger axial displacement, it means that the specimen will build up a lower compressive force, and definitely later on during the test. So from this slide, we also learn how important is actually the boundary condition, because the numerical substructure at the end of the day is representing our boundary condition during the test. Okay, and this brings me to the last slide, which are the conclusions and future work. And I think that first of all, by just analyzing this type of assemblies, wall assemblies, we learn that the thermomechanical behavior is dependent on the heating rate and the restraints from the numerical substructure. And it was nice to see, as I said, some forces and displacement in this type of material, which is not very easy to find in the literature. And then I think it was, for us, it was nice to see that we were able to perform hybrid fire tests. And as I said, because it's quite challenging to develop this methodology and all setup. And by performing the test, we were able to tackle a problem from, as I said, from a different perspective, and which is more economical solution at the end of the day compared to the full-scale testing. And because we still don't know how to model the gypsum plasterboard numerically model or to predict the failure mainly, I think that this exercise also helps us understand a bit more about the thermomechanical behavior, and therefore probably developing some models in the future. In terms of hybrid fire testing, so we consider for the beginning 1 degree of freedom problem, but in reality, most of the times we have multi-degrees of freedom problem. So I think this will be one of the points that we will focus in the future. But at the same time, the numerical substructure, the way we model the numerical substructure can be more complicated. And I think that's also a point that we will be looking into it in the future. And this brings me to the end of my presentation. Thank you very much. And yeah, I'm looking forward to hearing your questions. And if you have any questions, I don't know, in the coming days, don't hesitate to email me.
Thank you very much, Anna. Very nice presentation, and a virtual round of applause from me already. And indeed, as I mentioned at the beginning, it would be good now if we get some questions in the chat box. That would make it a structured way of asking questions. We started a few minutes late, so I will allow for a few minutes of questions. Well, maybe somebody, okay. So we have a question. Have you already done similar tests, but focusing on the behavior of the connections?
No, we didn't do any test that focuses on the behavior of connection, but I think that's something, yeah, that's a good point and a good question. And I think it has quite a lot of potential there.
Okay, so future work.
Yeah, definitely.
Maybe I can also already ask a question while maybe somebody else is typing. Are there any limitations on the heat transfer from the, let's say, physical substructure to the numerical one, or is that not an issue?
I think there shouldn't be any limitation because yeah, that's a good point. During our exercise, for simplicity, we just consider that numerical substructure stays at ambient temperature, but we can consider actually the transfer from the physical substructure to the numerical substructure. So that can be done, and it shouldn't be. It is possible, so it shouldn't be difficult.
Okay, thank you. I will leave 1 more minute to see if something else pops up in the chat box. In the meantime, I could ask Ben to prepare for setting up his presentation.
Okay, so I will stop sharing my screen then, maybe?
Yeah, I don't see any questions popping up. 10, 9. No, so then thank you once again, Anna, for a very nice presentation. Very inspiring, I would say, and I look forward to future applications in practice, but also, of course, in research. So thanks a lot.
Yeah, thank you also.
And then it's my pleasure to introduce the second presenter of this evening. That's Ben Atkinson, now with Jensen Hughes. I don't know, Ben, if you're ready to share your screen and your presentation while I'm introducing you. And I'll tell the audience that you will tell us something on how to deal with single stair buildings, to be more precise, single stair office buildings, and how to do that with a performance-based design approach. So Ben, I see your title slide on the screen now, so I assume you're ready to go, and therefore, without further ado, the virtual floor is yours.
Thank you, Bart. Can everybody hear me okay?
Yes.
Good stuff. Okay. I think I was introduced as being with Jensen Hughes. It's a minor point. We are still Jeremy Gardner Associates, or JGA, at the moment, although we're part of Jensen Hughes, so there probably will be a name change sometime next year, but let's not worry about that. So yeah, I'm going to talk about a practical application of modelling to deal with a particular particular fire safety problem. Single stair office buildings. So I'm going to talk about the background to the issue. Why is this an issue of interest? Code guidance applicable in the UK, and then the fire engineering factors that we need to consider when developing a performance-based design, essentially. And then what are we trying to achieve with the modelling, and in what circumstances is it necessary? And then finally, I'm going to talk through an example of a modelling example applied to a real project, which involved evacuation modelling and smoke modelling. So to start with, I'll talk about the code guidance applicable in England and Wales is quite restrictive. It is only guidance. Performance-based design is quite well established in England and, well, throughout the UK. And it's not obligatory to follow the guidance documents, but obviously they give you a starting point when looking at a new project. So with respect to office buildings and other commercial buildings, it is very restrictive. With a single stair, the maximum permissible top story height is only 11 metres. Once the top floor is more than 11 metres above ground, 2 stairs are recommended to comply with the guidance. As some of you may well be aware, single stair residential buildings are permissible in England and Wales of any height whatsoever. It's obviously quite a contrast. There's another guidance document that deals in particular with blocks of flats and dwellings. And this is based on what's known as a stay put strategy, a high degree of compartmentation, and some form of smoke control to protect the stair from smoke, should people choose to evacuate. This has obviously come under a lot of attention following the Grenfell Tower fire, and it will be a subject of further debate and possible changes to guidance in the future. Since Grenfell, Scotland, which has a separate building control system, has changed its guidance to recommend 2 stairs above a height of 11 metres, I think, and it's possible there will be changes in England and Wales in the not too distant future. So back to the topic at hand. Why would we want to design an office with a single stair and with a top floor over the 11-metre threshold? Well, the short answer is that there is a demand. The first point is entirely commercial. There are, certainly in London and other cities in the UK, there are lots of small plots where putting in 2 stairs as opposed to 1 could be the difference between a project being financially viable or not being viable. So it makes developments on small plots much more efficient. The other, I guess, key aspect is there is a large stock of existing buildings with unconventional escape routes, typically via adjoining properties. It's not uncommon to find buildings with a single stair and sort of at or around the 11-metre height mark, there might be a separation within the stair enclosure, a door partway up the stair, with the idea being that those on the top floors have the option of either going down the stair and out to the street at the front of the building, if it's safe to do that. But if there's a fire below them and smoke is affecting the stair, they've got the option of then going up the stair onto the roof, and from the roof somehow getting into a neighbouring building and down via the escape routes for that neighbouring building. Now that latter option has all sorts of problems associated with it. Security is probably the main one. For security reasons, obviously people don't want people from next door escaping into their building. It really doesn't work very well. So aside from the purely commercial reasons for wanting to develop a strategy with a single stair, there are sound technical reasons. It's possible to develop a single stair strategy which is much more robust and reliable than a design which relies on escaping to a neighbouring building. So when we're thinking about this issue, what do we need to consider? Well, I think the main factors, sort of building factors, if you like, are occupant characteristics. Office occupants should be awake and they should be familiar with the building, familiar with the escape routes. So in terms of their response to to a fire alarm signal, they should be, I guess, the best type of occupant, if you like. They should respond quickly and get out of the building quickly. Building height's obviously a key factor. If we're adopting a fire engineering approach, we don't necessarily need to, the 11-metre figure I talked about earlier isn't necessarily relevant, but when considering an alternative approach, I think how far you are away from what the code recommends is obviously a key factor, both in terms of whether it's a viable option, whether it's a technically sound option, and whether it's one you're going to get approved through the approving authorities. Another important factor is the size of the floor plates. Code guidance recommends only up to 18-metre travel distances in a single direction, which you've almost inherently got with a single stair, and a maximum of 60 occupants with a single exit. Now, it is possible to vary those figures based on fire engineering principles, but I think it is fair to say that when you're developing a strategy for a single stair office building, it's only going to be viable with a relatively small floor plate. So aside from the sort of building factors, we've got to consider what we can add to support a single stair office strategy. Automatic fire detection and alarm is a relatively straightforward one. It's standard practice to include automatic detection and alarm in significant office developments in the UK. However, going back to the code I referred to earlier, that's not an expectation of the codes. It's perfectly permissible to design an office building with 2 stairs, a stair at either end, for example. It could be just under 30 metres in height, top story height, and that wouldn't require automatic fire detection and alarm. It would require an alarm system, but that could be a manual system involving break glass units or similar. Compartmentation is obviously an important factor. Going back to the code guidance for residential buildings I talked about earlier, that's clearly a key factor as to why a single stair is permissible for residential buildings. And the idea is fairly simple. Smaller compartments means a smaller fire. And some of that can be applied to an office development. Suppression, such as sprinklers or water mist, I guess that performs a similar function. The idea being that if you suppress the fire, the risk to the stair is controlled. You're controlling the quantity of smoke produced and the hazard it represents. And then finally, smoke control. Some form of protection to the stair is likely to be necessary. Typical options are pressurization, smoke extract from the office floor plates is an option, and probably the most commonly used one is, certainly in the UK, is lobby smoke extract of some description. I'll explain a little bit more on that, as I gather it's more widely used in the UK than elsewhere. But the idea is, see where the cursor is here. This is the fire floor. Then between the fire floor and the stair, there's a lobby, and here there's a vertical shaft running up to the roof level with fans on the end of it. And the idea is that the shaft system draws smoke from the lobby and up out to the roof, and we have an inlet via a vent at the head of the stair, which draws in clean air from outside the building, and that serves to minimise the risk of smoke spread into the stair. The mechanical system I'm showing here, that was developed by various manufacturers, Colt probably being the best known one over the last, I think it's probably around 15 years ago. This follows on from a development by the Building Research Establishment, who were looking at protection of firefighting stairs, firefighter access stairs from smoke, and they developed essentially a natural system. that did the same thing, based on a natural smoke chimney. The drawback with that system was that the chimney size required was 3 square meters, which took a big chunk out of the floor plate. Various manufacturers, as I said, then developed a mechanical alternative, which does much the same thing, but because it's mechanically assisted, it's only requires a shaft size of around about 0.6 square meters, which is obviously much better in terms of the impact on lettable floor area. So these systems, they tend to use an extract rate of about between 3 and 5 meters cubed per second, and they have pressure sensors in the lobby, so the extract only kicks in when the doors are open and you've got the inlet from the stair, and that avoids excessive depressurization, which can lead to doors being difficult to open and problems such as that. So I'm going to pose this question here and come back to it. Lobby extract systems, such as the one I showed there, they're designed and they're quite extensively validated to prevent smoke flow into the stairs during firefighting operations. Similarly, a pressurization system would be designed to meet the British and European standards to protect the stair during firefighting operations. So I think why do we need to carry out modelling? I think it's a fair question, and as I say, it's one I'll come back to. So moving on to the project example, this is probably at the upper end of where this sort of approach is feasible. We're just over 30 metres to top floor height, sort of 500 square metres per floor, which works out about 90 occupants per floor, using UK guidance, and 2 exits into a stair lobby on each floor, but from the lobby there's only 1 exit into the stair. Mechanical smoke extract from the stair lobby, and sprinkler suppression on the office floor plates. And this approach was supported by evacuation and smoke modelling. So the evacuation modelling has 2 objectives. The first one is it sort of interfaces with the smoke modelling, if you like, to establish a timeline for evacuation of the fire floor, and that then informs the door openings, which need to be input into the smoke modelling. The second objective is to come up with an estimate of the time taken to evacuate the building, and this can be used to identify whether there's an issue with occupants evacuating, obstructing firefighters arriving to deal with the fire, a sort of contraflow, if you like. I think this is an example of a fire engineering approach being held to a higher standard than a code compliant approach. You can design going back to the sort of 29 metre high building I talked about earlier, that could be designed with 2 stairs absolutely full to capacity, 1 or both of which might be used by arriving firefighters, and there would be a contraflow issue, but that's a code compliant solution, so it's not something we'd be asked to look at. But for an engineered solution, I think it's quite common to be asked to go the extra mile, if you like. So this is a still from the evacuation modelling. This was using the Pathfinder model. So what we can see here, this is the blue area is the office floor plate. This area here is the single stair, and here we have a lobby with an exit into the lobby here, and an exit into the lobby here. The Pathfinder gives you some quite nice visuals, and actually can produce some quite nice videos, but I thought better of trying the videos over the internet. But I think the visuals it produces are certainly a significant advantage when talking through a fire engineering approach with approving authorities. So what we can see there, we've modelled every floor plate and obviously the single stair itself in order to come up with an estimate of the evacuation time. So the results from this model were that the fire floor was evacuated within around 3 minutes. Everybody is into the stair enclosure within around 11 minutes, and the building is completely empty of occupants within 25 minutes. I say item 1 then feeds into the smoke modelling we carried out, which yeah, here we are on the next slide. This is the as I touched on earlier, the lobby extract system is configured to only run when there's a source of replacement air to avoid depressurizing the lobby excessively. So when the doors are open during the evacuation phase, the lobby extract ramps up over a period of around 30 seconds. Then it stays at full speed. In this case, it's 5 meters cubed per second during the evacuation phase. Once the evacuation of the fire floor is complete, it then shuts down again until around about 15 minutes. And that's an arbitrary figure. It's an estimate, if you like. We assume firefighters arrive on site and on the fire floor ready to tackle the fire. So again, we've got a ramp up of the extract rate over around 30 seconds, and then it runs full speed during firefighting operations. So moving on to the smoke modelling, this was carried out in FDS. The smoke modelling only covers the fire floor and the stair because that's all we're interested in terms of smoke spread. On the fire floor, it looks very similar to the evacuation model. We have a fire fairly centrally located and quite close to the lobby, which represents I guess a reasonable worst case with respect to smoke spread into those areas. In terms of results, this is during the evacuation phase, so it's just showing smoke density in terms of a sort of grayscale visualization. So this is a fire here where the smoke is obviously denser. We have smoke spread into the lobby, which you can probably just about make out here, but we don't have smoke spread into the stair. It's completely clear, which shows the lobby extract system is doing its job. And we can also overlay the smoke results, the evacuation model results. As you can probably see, this is towards the end of the evacuation of the fire floor. So these dark blobs you can make out here are if you like, the stragglers, the last few occupants leaving the fire floor. They're currently in the stair lobby, and the stair, as you can see, is fairly busy with people from the fire floor and also from floors above. At this stage, we're just about approaching the end of tenability on the fire floor. The black line is showing a sort of 5 meter visibility contour at 2 meters above head height. So it's not completely untenable yet, but we've got quite a lot of smoke, and I think it's as it would suggest, everybody probably ought to be off the fire floor by that stage. So we then moved on to the firefighting phase. Clearly, the fire's been burning away for 15 minutes. At that stage, we've got hot dense smoke, fairly hot dense smoke throughout the compartment. When firefighters arrive on site and open the lobby door, whether it's this one or that one, the lobby is quickly sort of filled with smoke, as you'd expect. At that stage, we also get what you might call a plug of smoke flowing from the lobby into the stair. Now, this isn't necessarily a problem. It's fairly short-lived. We can see this again in using a bit of colour. Here's the fire floor, full of hot dense smoke. This is a visibility scale. So red is sort of 1 to 2 meters of 2 meters visibility. This is the lobby on the other side. Again, very low visibility, and this is the plug of smoke flowing into the stair when firefighters open the door. As I say, it's a fairly short-lived issue, and it quickly clears once the once the lobby extract system ramps up to full speed. And I think there's a question mark over the assumptions we made in the modelling. I think if firefighters wanted to avoid this, they could open the doors perhaps in stages, such that the extract system has time to ramp up to full speed. But either way you look at it, it's not a significant problem for firefighters in practice, because it's only a fairly short-lived transient bit of smoke flowing into the stair, which is quickly diluted. So to conclude and come back to my earlier point, what's the point of modelling? And I think it'd be fair to say I don't think it's necessarily needed in every case, but certainly for the projects or the fire engineering strategies that vary further from the code, it probably is needed. It does give you the advantage of it is project specific. It's a bespoke analysis. You can consider unusual geometries or ceiling heights. You can carry out sensitivity analyses with larger fires, different fire locations. I think for pressurization systems as well, the impact of doors being open on multiple floors during evacuation is something that is well worth considering during the modelling. But I think perhaps most importantly, the current climate in the UK is that modelling is increasingly expected. That's probably partly a post-Grenfell effect. I think approving authorities are more nervous than they were before that, for understandable reasons. I think also it's becoming more routine and accepted. And going back to the evacuation modelling, for example, in some cases it's quicker to run an evacuation model than to do it by hand calcs. I mean, I've been doing this job for long enough that I remember doing an evacuation model of a building on using an Excel spreadsheet, and that took quite a long time. And it's actually much quicker to stick some numbers into a model such as Pathfinder, and you get the result much more quickly. So I think increasing use of modelling is very much the way things are going for various reasons. And I think that's more or less it for me. So I'll conclude there. And if you have any questions, please shout.
Thank you very much, Ben. Also from my side again to you, virtual round of applause. Hear myself twice. I assume that's your device now. But if anybody has any questions, please do not hesitate to type your question in the chat box. It's a very nice illustration, by the way, of modeling in practice. There is already a question by Arnaud. I don't know if you can read it, Ben. Otherwise, I'll read it for you.
Yeah, if you could. I'm struggling to find the chat box today.
So the question is, in many engineering disciplines, CFD modeling is treated as a qualitative tool that is useful to compare different design solutions. And you are using CFD modeling as a quantitative tool. So the question is, how confident are you in the results?
I think with something like this, we are quite confident. Well, we're very confident, in fact. As I mentioned, there's a long history of, or quite a history of using this sort of smoke shaft solution to protect stairs. The BRE natural shaft solution was developed around about 20 years ago, and they carried out CFD modelling at that stage, and also compared their results with physical scale modelling. And then when various manufacturers developed the mechanical solutions, they also carried out fairly extensive modelling to show that their solutions worked. So there's a lot of data to compare the results we get with, to know that they're credible and make sense.
Okay. Thank you. And by now the chat box is exploding, so I'll just ask the next question from Andrea Luccherini, asking how many open doors you considered for the design of the lobby extraction system, and is it in accordance with the fire safety strategy, like, for example, cascade evacuation?
We considered the two open doors on the fire floor from the fire floor to the lobby, and the one open door from the lobby to the stair. I mean, I think that's one of the perceived advantages of the lobby extract systems over pressurization. In the pressurization systems can suffer if you're pumping air into floors which don't have a fire, whereas the lobby extract system has the advantage that it's only extracting on the fire floor.
Mm-hmm. Okay. I will make a selection because we have really many questions now, and I suggest that some of the questions may be replied afterwards, but I'll just ask the next one, which is a technical one. Do you remember what kind of soot fraction and fire growth was assumed in the model? Do you remember that, or it's quite a specific technical question?
It is point one is the soot fraction,
Okay.
which is more or less standard.
Mm-hmm.
And very much what the approving authorities expect.
Okay. And the fire growth, was it fast or was it?
It would have been medium and then controlled by the sprinklers at again okay. UK fire engineering guidance certainly suggests medium for an office.
Okay. Good. Thank you. Then there was a question by Farah. By the way, most people thank you first for your presentation. So the question is here, why a pressurization system class B hasn't been considered? Like with a lobby extract system, the system would pull out the smoke into the lobby and then relies on the doors being closed at specific periods. And that might be acceptable if there is an alternative in a two-stair design, but in a single stair design building, the risk of the stair being compromised is higher. So the question is then, coming back, why a pressurization system class B hasn't been considered? I assume according to 12.101/6.
Yeah, I mean, I think it has been considered, and I think it's fair to say the climate is changing, and certainly with respect to single stair office buildings, there was a consensus between fire engineers and approving authorities that a lobby extract system is good enough to do the job. I think that may be changing, and I think it's fair to say pressurization is being asked for, being considered much more. I think in the UK, pressurization isn't widely used. It's got the reputation of being difficult to design, difficult to commission, and from a, I guess, cost and buildability point of view, these lobby extract systems have been very much the favoured options.
Okay, thank you. A very short question: is dead end considered for a single staircase?
So is what considered?
Dead end, like I guess that like you get stuck somewhere. I assume that's what the question means.
Well, no. The staircase is considered a place of relative safety,
Okay.
and the whole strategy is about making sure that it remains tenable for escape during evacuation. I think there are lots of side issues, particularly in relation to escape for people who can't use the stairs, which I haven't had time to go into here. But they also obviously all need to be considered.
Okay, because that was one of the other questions that I see here, like how was the lobby made safe for occupants who can't use the stairs, so using the lobby as a refuge point. Was it made safe, or was that not considered here? The lobby itself.
The lobby is relatively safe. I mean, during the evacuation period, there is some smoke flow into the lobby. It's not kept completely smoke free. Wheelchair users could also be in the lobby at the period, but the strategy generally adopted is to use there are lifts provided for firefighters to use, and prior to firefighters arriving on site, they could be used to assist with the evacuation of people who can't use the stairs. So that would be prioritised, with those on the fire floor being helped out of the building first. So any exposure to smoke should be very limited, and certainly no worse than that for those who are able to walk.
Okay, thank you. I'm going to combine two questions here, one from Ming-Chang, one from Enrico. One question is validation of the results of the modeling usually required by the authorities having jurisdiction? And the other question is, how would you recommend to treat uncertainties, particularly in evacuation modeling in this type of applications, because the results would vary presumably vary a lot with different assumptions, for example, on the pre-evacuation response time. So is validation typically required or not, and how would you treat uncertainties?
Validation is usually required to some extent. Increasingly, third-party reviews are being required. Sometimes the approving authorities, the AHJ, will have the expertise and carry out their own review. So it's increasingly common. So, sorry, could you repeat the second part again?
Yes, how would you treat uncertainty in evacuation modeling? So in particular, the pre-evacuation response time, for example.
Yeah, we'd consider a range. I mean, there are fire engineering guidelines for the UK, BS 7974, which gives specific guidance on issues such as pre-movement time, pre-evacuation time. I think in this particular case, the overall evacuation time isn't particularly critical. It's more the evacuation of the fire floor, and I think although the British standard does give these figures, I think they're widely as being conservative. For example, they assume that on the floor of a real fire that's developing relatively quickly, but there's still a significant pre-movement time of 30 seconds to a minute where people stand around looking at it rather than evacuating. And I think in an office environment that is probably quite conservative.
Okay, and unless I missed one, I'm coming now to the final questions, which have been asked by the same person. So it's about the 5 meter criterion. Well, I'm not sure if you used it as a criterion, but the 5 meter ISO line that you used for in the visibility plots. Like where did you use that, and why did you take 5 meter? And there was a follow-up question: how did you decide on the visibility C factor? I think we call it K factor as well in the simulations. I assume the answer to the last question will be the default settings of FDS, but then the question is like, why did you choose the 5 meter line? And if the visibility factor was not the default one, then please also comment on that one.
Yeah, the visibility was the default. The 5 meter line that I showed, that was just an illustration. It wasn't a pass-fail criteria as such. I think what that slide showed is quite interesting in that if you were to model a fire in many enclosures that fully comply with code guidance and follow the fire engineering guidance in terms of fire growth rates, pre-movement times, etc., you could show that many arrangements that fully comply with code guidance are not safe, in that the tenability criteria would be exceeded before everybody gets out. In that one, so the 5 meters wasn't a pass-fail criteria. As it happened in practice, everybody was in the stair lobby at that point. So it was shown that everybody's got out before things became untenable. But I think it was, as I say, it wasn't intended as a pass-fail criteria.
Okay. Thank you very much, Ben, for these replies. And I assume that everybody has had enough time to type their questions if there were any remaining questions. So I take for granted that this is not the case. And I'd like to thank you again, Ben, and also you, Anna, for the very nice presentations again. I think I can speak on behalf of the entire audience, and it's confirmed in the chat box by many. Nevertheless, I also remind the people attending that, particularly also Anna, I invite you to ask by email if you want, and I trust the same holds for Ben. So if you have still burning questions that you didn't dare to ask, thanks Ben for confirming. If you have questions that you didn't dare to ask now, feel free to contact them. With this, I'd like to thank you all for being present. It's always a pleasure to see so many familiar names, albeit in a virtual way, and I'll be very happy to see you in person as soon as we can. So until then, I wish you a very nice evening or rest of the day, wherever you are on this planet, and stay safe and take care. Bye-bye.